Hello, Honors Math 2. Today we wrap up this Module 1. Next week we will review and then test on Module 1. Let's see, quick review. Can you solve these exponential equations from last time? Remember, to solve exponential equations, we try to get the bases the same. Okay, so let's get the same base on the left and the right. Pause and find that base. Notice that same base that I get is 3. This is 3 to the x minus 7. I can rewrite 243 as 2 to the 5th raised to the x. That means that I can set my exponents equal to each other, and x minus 7 is equal to 5 times x. I get that 4x is equal to negative 7, and x must equal negative 7/4. Alrighty, please try to notice what base I need in that next case, and I'm going to force those bases to be the same. I'm going to rewrite both sides with a base of 5. This stays 5 to the 2x plus 1. 1 over 125 is actually 5 to the negative 3rd power. Then multiply those exponents, and I'm left with 2x plus 1 is equal to negative 3x. Let's get those x's positive. 5x is equal to negative 1. And you should have gotten x is equal to negative 1/5. Okay, sometimes those are tricky. Thanks for refreshing your memory. Alrighty, can you please start to find the inverse of this function, and then we're going to graph both this function and its inverse. I think I would like to list the domain and the range of this function first. Notice that with a square root function, what kind of numbers can you have under the root, and that's going to give me the domain. Notice x minus 3 needs to be what? X minus 3 needs to be positive, so greater than or equal to 0, and x has to be greater than or equal to 3. Gives me a domain from 3 to infinity. Okay, let's graph that square root function. Is that a shift up, down, left, or right? That root is going to shift to the right 3. 1, 2, 3. And then I'll get that hook function when I graph it. Over 1, up 1. Over 1, 2, 3, 4, the square root of 4 is 2. And I get that hook to the right. Make sure you label so you remember that's f of x. Okay, so now we're going to find f inverse of x. Remember, I rewrite that function up above as y is equal to the square root of x minus 3. I switch the x and the y so that the inverse is x equals the square root of y minus 3. And I'm going to ask you to solve for y. I'm going to square both sides to undo that root. I'm left with x squared equals y minus 3, and add 3 to both sides. Y equals x squared plus 3. Write that in inverse notation. F inverse of x is x squared plus 3. And I'm going to list the domain and the range of this inverse function. Notice the domain of my original function becomes the range of my domain of the original becomes the range of the inverse, and vice versa. What was the range of this original function? Notice my y values start at 0 and go up, so the range is 0 to infinity. That means that the range of that original becomes the domain of this inverse function from 0 to infinity. Oh, so that's a quadratic with a limited domain. It's a quadratic function starting at 0. I shift up 3, right 1, up 1, right 2, up 1, 2, 3, 4, and it also checks with the range, and the range is from 3 to infinity. And label that as f inverse of x. So you recognize the two. The inverse can never get larger than the original. The inverse can never contain more points than that original function. Alrighty? Alright, good practice. Take a moment to graph this exponential function. Do you remember for an exponential function, we had certain points that we always plug in, x, f of x. Find those points and plot them. And then I'm going to list the domain and the range of this exponential function. Notice 3 to the first is 3, 3 to the 0 power is 1, and 3 to the negative 1 is 1/3. I plotted those points. Notice the domain. I can plug in absolutely anything from left to right for x, so that's negative infinity to infinity. but the range of values, my y values start at 0 and go up. And notice I'll never touch y equals 0, so the range is from 0 to infinity, and we scooch along that asymptote. That asymptote is horizontal, so it's a y is equal to 0. Okay, now we're going to find f inverse of x. I'm going to rewrite as y is equal to 3x. I'm going to switch my x and y, which is x is equal to 3 to the y, and solve for y. I'll pause so you can do that. I'm hoping solving for y here, you're having a little trouble. I've seen people say this, the opposite of raising to the y power is taking the y root of both sides, the y root of x, and they're left with, what is that? 3 is equal to the y root of x. I mean, it's a creative idea, but then how do I get y out of that root? Okay, so we don't do that. All right, so we're kind of stuck right here to solve for y. I'm going to write myself a little note. To solve for y, I'll be honest with you, mathematicians had to make something up. And the notation that they made up to get that y out of the exponent is a logarithm. So here, to rewrite that, we introduce a logarithm. And bottom line, a logarithm is an inverse of an exponential function. A logarithm is an inverse of an exponential function. And the notation we make up is this. I'm going to rewrite this exponential as a log with the same base. The base of that exponential is 3. The base of the logarithm is 3. It's a little subscript. And I switch the x and the y. So the base stays the same, but the x now goes with the 3, and the y is isolated. So again, we made up this notation to isolate that y, to get that y out of the exponent. So the inverse I'm going to write as f inverse of x is equal to log base 3, it's a subscript, of x. And we introduce that logarithm notation. Now I don't really have to know anything about plotting points on that, because remember the points on this inverse, let me write this as x f inverse of x. I can still do that switching. If these points were on the original, then the reverse of those is on the inverse. So I can write these as 3, 1, 1, 0, 1/3, -1. Take a moment to plot those if you would, and then notice the domain and the range of your logarithm. I'm going to pause, and voila, would you look at that? There's my original exponential. Here's my logarithmic function. Notice the domain, my x values are starting at 0 and going off to the right to infinity, 0 to infinity, which checks out. That was the range of my exponential. And my the range now of my logarithm can be anything from -infinity to infinity, which was the domain of this function, the original function. So they do switch. Notice the asymptote. Can you tell what this is scooching along? That logarithmic function now has a vertical asymptote. Is that an x equals or a y equals? That asymptote should be x equals 0. All right, so we introduced this notation to get that variable out of an exponent. We introduce a logarithm notation. And you can see that symmetry across the line y equals x. That a logarithm is the inverse of an exponential. Okay, let's explore these logarithms a little bit more. Okay, for your reference, you can read a little bit about a logarithmic function, but bottom line, this notation, y equals log base a of x, I will typically read that as log base a, log base a of x. Log base a of x. This is when we use a logarithm. If I ever have x is equal to some number to a power, and I need to get that variable out of the exponent, then I rewrite this as, again, it's just introducing this notation. If I have to get that variable out of that exponent, I rewrite that as log base a, base stays the same, but then I switch. The a was with the y, now it's with the x, And these two things, just so you realize, are perfectly equivalent. They mean the same thing. I will always call this same base switch. So you're going to hear me saying that a lot over the next few days. Same base switch. So the base stays the same. Base of the exponent becomes the base of the logarithm, but then I switch. The a was with the y, now it's with the x, and I switch that x and the y. Okay, let's get a little comfortable with that same base switch. If y is equal to log base 3 of x, then this is perfectly equivalent. Just another way to write that with an exponential notation. What's the base of this logarithm? The base of that logarithm is 3. So that becomes the base of an exponential. And I'm going to same base switch. The base stays 3, but the 3 was with the x. Now the 3 is going to be with the y. And those two things are perfectly equivalent. Two different ways to write the same thing. This is equivalent to what? Same base switch it, please. If y is equal to log base 5 of x, that's equivalent to same base as 5. 5 was with the x, now it's going to switch and it's going to be with the y. And those are equivalent. Okay, just for a little practice getting comfortable with our logarithms, here's some exponential expressions. Could you change them to logarithmic expressions by same base switching them? Please rewrite that as a logarithm. Give it a go. Alright, just getting comfortable. The base of the exponential is p, so that becomes the base of the logarithm. I'm going to switch. P was with the 3, now it's going to be with the m, and those two things are equivalent. That's a subscript. It's written a little bit lower. Everything else is nice and even. Rewrite this one. That's log base, same base, so the base is going to be a, switch. The a was with the 4, now it's going to be with the 24, and those things are equivalent. The base of a logarithm, this is important, the base of a logarithm, where is it? The base of a logarithm is always positive. We use positive bases in that exponential function. So the base of a logarithm is always positive. Basically because I can't take a root, an even root of a negative number, if that was like a 1/2. So I can't take an even root of a negative number. So the base of a logarithm is always positive. Try just for a moment to go the other way. Can you rewrite this now exponentially? Same base switch it. And we simply rewrite those next two expressions. I'll pause. Rewritten as an exponential expression, the base stays the same. The base here was a, the base here is a, but switch. A was with the 4, now it's with the 5. Those are equivalent. And base here was 3, but the 3 was with the 5, now it's with the c, and those are equivalent, logarithmic or exponential. Okay, we can use that property of rewriting to say there's a value for this. What is the value of log base 2 of 16? That's just a value. Watch this. What would that be? What would that value be? Can you take a second and rewrite that exponentially, please? Let me rewrite that. So same base, 2, switch. Now the 2 will be with the x when I write it exponentially, equal to 16, and solve that little equation. Oh, you need to get the bases the same. Or you just see what it is. Please solve that. 2 to the x is the same as 2 to the 4th, so that exponent must be 4. So the value of that expression is just 4. What's the value of this expression? I say 3 to what power equals 1 over 27. 3 to what power, same base, switch, is equal to 1 over 27. Take a moment and solve that equation. This 3 to the x is the same as this, which is 3 to the negative 3. So x must equal negative 3. And the value of that logarithm is negative 3. 3 to the negative third equals 1 over 27. Can you take a moment and write the inverse of this exponential function? You'll need a logarithm. Switch that x and y. When I switch the x and y, I can't get the y out of the exponent without a logarithm. Same base, log base 5, switch of x is equal to y minus 4. Let me pause to save time. I add 4 to both sides, and I just isolated y. And there's my inverse. Let's try that again. Find the inverse of that function. As we run out of time, you can check. Have a great